Yeah.
Right. Thanks a lot for the introduction. It's a great pleasure to be able to well, attend virtually and give a talk to the Advances in Data Science event. I think it's a really important event for the AI community in the North, and I always really enjoy participating. Actually, I participated in person in 2018 and 19. Unfortunately, I couldn't be able to be in Manchester today and see all friends, Mauricio and Magnus. But well, hi to everybody. So right, my talk today is on how we can improve explanation faithfulness in natural language processing. Mostly, I'm just going to present to you work that has been done by my PhD student George, who happens to have his viva in 2 days. Right, I can actually, right. Oh, I have to click on the slides, right? Okay, right. Can you see now the second slide? Yep.
Yeah, we can.
Oh, cool. All right. Yeah. No
background,
problem.
if that's the same.
All right. Yeah. Okay. Let's start with some background on explainability in machine learning, especially on supervised machine learning settings. Right. So let's begin with a definition of a rationale. What is a faithful rationale? A faithful rationale or explanation is a subset of the input that actually corresponds to the true reasons behind a model's prediction. So when we try to extract rationales, we try to identify the most important parts of the input that contribute to a particular prediction made by the model. And actually, this definition helped quite a lot on grounding work in interpretability in NLP. It was a definition by Alan Jacobi and Yoav Goldberg, a paper published in 2020. Well, interpretability work didn't start in 2020, but actually this is like a first definition on what is a faithful rationale. Okay, so now let's move to how we can extract rationales, and I will focus on. I'm just going to give a general picture on how we can do that in supervised machine learning settings, but I'm just going to use examples from natural language processing because actually I do natural language processing research. Okay, so in a typical supervised classification setup, we have some data. We train a model, and then during inference, we pass new data through the model, and we take predictions. In a typical natural language processing pipeline, for sentiment classification, for example, we have data that correspond to movie reviews. We pass them through a model. Typically, these models now are pre-trained transformers fine-tuned on that particular task, and we take predictions for the input. For example, the model here predicted that the sentiment of this movie review is positive. But the question is why the model made this particular prediction, why the model decided that this corresponds to a positive movie review. You can see actually here that it might be easily predict a negative review if the aspect was about cinema, but actually a good reason for predicting the positive sentiment if you are a human, you could say, well, because we have the word amazing and the word movie here, actually that might be a good indicator of the positive class. So actually we want to predict we want to extract this subset of the input that contributed to a particular prediction. Here actually I'm not going to make distinction between what is plausible by humans and what is faithful for the model, what actually the model decided that is important. Okay, so I'm not going to make, I'm just going to make this particular distinction, and we're going to focus only on faithful rationales. We don't really care actually in this work how plausible are the rationales for humans. All right, this is actually a different standard of work that actually we haven't looked at. Right. So there are two very popular approaches for extracting rationales. One is called post hoc explanation methods or feature attributions, as you can find them in the literature. The idea here is that you have a pre-trained class, you train a classifier on your task, and then after the training, and after the prediction, you apply a feature attribution method to identify which parts of the input are the most important for the classifier to make a particular prediction. So these methods compute an important score for its input token. I mean, this could generalize in any machine learning setup. Actually, I'm here I use examples from natural language processing. So the input usually consists from text. So we try to assign important scores to input tokens. So one group of feature attribution methods is called attention-based. It's based on the attention mechanism in modern transformer models. And actually, we have various ways of computing attributions. I give some examples here. One is just use the attention score that the model computes from the multi-head attention in a standard transformer, or we can compute the scaled attention by multiplying the attention score with the gradient of the attention. Also, there are specifically gradient-based approaches such as deep lift, integrated gradients, or actually just compute the gradients with respect to the input. I'm not going to give. There are many different feature attribution methods. Here I can just give you a flavor of these different two groups of attributions. And the second approach for extracting rationales is through select then predict models, or how we call them inherently faithful models by construction. Here, these models consist of two modules. One is the rationale extractor, and the second is the rationale classifier. So in the first step, we have a component or a model that extracts the rationale, and in the second step, the classifier takes as input only the rationale and makes the prediction. There are two ways of doing it. One is end-to-end, for example, Hart-Kuma, and also some more recent work, Spectra, actually published from Andre Martin's group that he gave a talk earlier today. And also disjoint two-step models where actually the rationale these models are not trained end-to-end. You have a rationale extractor first, that could be a feature attribution, and then you use the rationale to train a second model, for example, a BERT, only on the subset of the input that is important, only on the rationales. And actually a good example of these models is first published by Jane et al. In 2020. And of course, there are many others in the literature. I'll just give you again a flavor of what kind of methodologies we can use for rationale extraction. So now I have given you an overview, an idea of what is a rationale, how we can extract rationales in a typical supervised machine learning setup. The question here is, okay, how we can assess if the rationales are good, how we can evaluate the faithfulness of those rationales. So for post hoc methods, there are metrics such as sufficiency and comprehensiveness. Actually, just, well, I have added some equations here. I mean, it's not something complicated. We just measure the predictive, for sufficiency, we just measure the predictive, the difference in predictive likelihood given the whole input minus the predictive likelihood by just taking as input only the rationale. And for comprehensiveness, again, it is the difference between the predictive likelihood using the full input minus the likelihood of predicting the class given the input minus the rationale. All right, so we have those metrics. Actually, you can find them in the literature called fidelity measures. And we're going to talk a little bit about those later and how much we can trust them in out-of-domain settings. So for the select and predict models, this is a bit more straightforward to evaluate. The idea is that we just measure accuracy or F1 or macro, micro, whatever the evaluation metric is used for the full text models, and we try to make those models as accurate as possible compared to the full text models. Okay. Right, so we now have the evaluation in place. What I'm going to talk about first is the strange case of attention as an explanation in natural language processing. So I don't know if you remember, there was a huge debate sparked by a paper published in NACL 2019 called "Attention is Not Explanation" by Sathak Jain and Byron Wallace, where actually they argued, it is a great paper, and they argued that we should not be using attention as explanation in the wild. This is something that we used to do in NLP up to 2019. And then there was another paper, a follow-up paper, "Attention is Not Explanation" by Sarah Wigriffe and Yuval Pinter, where they say, well, okay, attention might be explanation under particular circumstances. And actually, even this year, I saw a paper in ACL. It's a survey on the debate. Is attention explanation an introduction to the debate? And actually, there is a nice literature review, a complete literature review on how attention can be considered as explanation in natural language processing. Right. So, inspired by this line of work, we sat down with George and said, okay, what he should be doing for his PhD. And one idea was to improve faithfulness of attention-based explanation with task-specific information. Okay, that might sound complicated. It's not. The idea that we had is that these neural encoders, for example, transformers in natural language processing, they learn contextualized word representations. What does that mean? They mix information, and the vectors learn for each token from, for example, from birth in the vector space. They look very similar. They're very close. Actually, if you try to compute cosine similarity between vectors for tokens learned from birth, actually you can see that the values are quite high. And actually, this is what Tutek and Snyder in 2020 found. So from this previous work, actually, we thought probably it might be a good idea to introduce non-contextualized information to the model after the attention scores have been computed. So we introduce a new module that learns salient information for the task and incorporates that to the attention scores, to scale the attention scores. So here is an overview of the model. Actually, the gray part is a standard neural encoder. You have the embeddings of your text input. You pass them through the encoder. An attention mechanism learns the scores, the weights for each of these contextualized representations, and then you pass them through you create a context vector for the entire input. You pass them through the output layer for classification. So the idea here is to introduce a set of parameters for each word in the vocabulary. So this is like a vector as long as the vocabulary. And actually, what we do is basically we learn those weights, and we just weight the embeddings. So actually, we just pass the embeddings we just actually learn these weights, we multiply them with the embeddings, and then we sum together all the embedding dimensions to learn a saliency score for this particular word in the input. And then what we do is just multiply the attention score with this scaled factor, and we just pass it through the rest of the network for making a prediction. By doing that, actually, we found that this improves the faithfulness of explanations for various attention-based attributions. So actually here you can see that we use vanilla attention, the gradient of attention, and attention gradient attention, the scaled attention. And you can see that most of the times, by just using task, which is this component, actually produces way better results compared to not using tasks. So this is actually the percentage of decision flips by choosing the token with the highest importance. So actually, we just choose one token, we replace it, and we record if the prediction changes or not. Okay. Of course, I need to mention here, I mean, I just give you an idea of only the linear task. We have actually feature-based tasks and convolution tasks that they don't really work much better than the linear case. And the linear case, it's much simpler. You can find details in the paper. Right. In the same line of work, actually, now what I have presented you so far is learning task-specific information and try to scale it in the input level, right? So on the we try to first scale the embeddings and then use this information to scale the attention scores. Another way to do it is to introduce to actually learn some saliency information prior, like for example, what are the most salient parts of the input without using a supervised model at all, and actually use this salience distribution to get the attention, try to get the attention distribution close to this salience distribution to improve faithfulness. So now, instead of changing the encoder or introducing a new component in the loop, actually we just have an auxiliary loss function to improve the faithfulness. Right. Again, the same idea is we have information mixing, and we want to learn salient information to reduce this information mixing during that happens during training. So first, we compute token importance using text rank. Actually, it doesn't really matter. You can compute token importance for a particular input sequence with any unsupervised way. We found that text rank works quite well on early experimentation, and we stuck on that. It's very easy to compute. You just consider your text as a graph, and you apply page rank to identify which words are most important than the others in one particular document, in one particular instance. It's quite widely used in natural language processing for keyword extraction. So the idea here is to penalize the model when the attention distribution deviates from the salience distribution using an auxiliary loss during fine-tuning. So the idea is this. So we have a standard classification loss. You have your favorite transformer here, the input. You pass your input through BERT, and then actually we have the classification loss and the what we call salient loss, SAL loss. We try to bring together the attention distribution and the salience distribution that has been computed with text rank. And actually, by doing that, we found that empirically it works really well, especially for attention-based scores. Again, here we see the fraction of tokens removed to cause a decision flip. So the lower the better. It means that if I remove a smaller number of tokens from the input and we cause a decision flip, that means that those tokens are more important for predicting that particular class than the rest. So the lower the better here, and you can see that actually all the feature attribution methods here, gradient-based and attention-based, are improved. Specifically, attention-based metrics, actually we see that they work much better across different data sets, and this is by using standard BERT on those data sets. And the only thing that we do during fine-tuning, we introduce this auxiliary loss. Okay. Now I'm just going to change a little bit the topic, and we're going to see a little bit what happened with feature attributions, the strange case of feature attributions. So we saw actually that the problems with attention explanations and methods for improving attention-based explanation, and subsequently even gradient-based attributions. Here we're going to talk a little bit about feature attributions. One main problem is that when a practitioner trains a particular model, a supervised model, I don't know, fine-tunes BERT or Roberta on a data set, using post hoc explanation methods might be tricky because there are various choices to be made. One is what feature attribution shall I use? There is no single best across models, data sets, instances, or instances in the same data set. So actually, it is very tricky to just choose one of the self and be confident that actually it will work well on a particular task. Second, the rationale type affects the faithfulness. Shall I extract a phrase or independent tokens from the input? And actually, this is what has been done in previous work. Actually, all those methods are usually evaluated by extracting phrase-based rationales or independent tokens, top K independent tokens from the input. And the third one is how long the rationale should be. Previous work actually choose short rationales, but the cutoff usually is arbitrarily chosen. Not so much for select and predict models where you can actually learn the length, but for feature attributions, usually people say, okay, let's extract 10% or 20%, but what about if 5% is enough? We don't really know. So these are choices that need to be made, and it looks like a hyperparameter tuning setup where actually the number of combinations is very high. So driven by that, that we have to make different choices that affect the faithfulness of the rationale. We developed a simple method to extract flexible instance-specific rationales for natural language processing models. So given a set of M feature attribution methods, so you can actually have a large set of feature attribution methods, the ones that you think that might work well in your particular setup. And for each feature attribution in the set, we compute importance. We subsequently select the k highest score tokens to form a rationale. So we extract the rationale. So this first two steps is basically extracting rationale with one particular feature attribution. And for each rationale, we just compute the divergence between the reference model output using full text and having the rationale masked. So actually, we expect larger deviation if the rationale is good. And we select the rationale with the highest difference. And this is the case for selecting an attribution. You can actually repeat this process for different lengths and different rationale types. And actually in the paper, we show results where actually by taking into account all these three different dimensions, it improves faithfulness of explanations. So actually here you can see some results in across different data sets, multi-RC, AG, SST, and EBINF. You can see that actually with our method, you get much lower F1 macro, means that actually it selects good rationales. When we remove them, performance drops. For sufficiency, you can see again that our method, some data sets performs a little bit better, some others it's actually consistent with the best performing method. And for comprehensiveness, we see that consistently it is better than individual attributions. And also we have included the random baseline here. You can see that this is the worst across evaluation metrics. Okay. Right. And well, now I show you how we can select on the instance level better rationales. The final strand of work that we have done is to explore the faithfulness in out of domain settings. The idea here is, can we trust the faithfulness of rationales for predictive models in out of domain settings? The short answer is no, and we show that in a paper that actually George presented in ADSAI last month. The idea here is very simple. We try to see what is the faithfulness of post-hoc explanation methods and also the performance of select and predict models when we train a model on a data set in domain, and we measure the explanations, the quality of explanations in out of domain. So for post-hoc feature attribution methods, we train a model and we measure the faithfulness in out of domain held out data, and also in out of domain. So that could be IMDb, Yelp if we train on SST, and vice versa. For select and predict models, we train a model on the data set and we compute F1 macro, again, in domain and out of domain to compare both. Right, so we found, surprisingly, for in out of domain settings for post hoc feature attribution approaches, that faithfulness increases. And that sounds weird, right? So you cannot really have a model that is being evaluated out of domain and the faithfulness scores to increase. So we found out that, and that was really surprising. And what we suggested is a new way for evaluating faithfulness in out of domain settings, and actually probably in domain settings as well, is to compare it with a random baseline. So instead of actually reporting one score, we propose to use a random attribution approach as a yardstick and measure the difference between the feature attribution that you want to evaluate and the random baseline. Only if the attribution faithfulness is better than the random baseline, we can actually trust it as faithful. Well, for select and predict models, actually the results were as expected. Probably you can use them in out of domain settings without significant loss in predictive performance, which is actually really good. The problem with most of the select and predict models, it's that their performance is lower compared to using full text even in domain settings. So it's like a trade-off between performance and trusting the model predictions for those particular type of models. All right. So this is pretty much the work that we have done on improving faithfulness. And you might wonder, okay, why is that useful? And probably some people before me, some other speakers talked about why explanation is helpful and why we should care. So the first application that we looked at is legal text classification. That's a paper presented in NACL 2021 with collaborators from Athens University of Economics and Business. We actually try to extract rationales which consist of important facts, and these are paragraphs longer than what I presented so far, from a legal case to make predictions, and that's actually for legal text classification where the documents are quite long. And the second application that we looked at is machine translation. We try to use rationale extraction for quality estimation of machine translation. Instead of actually training models specifically for estimating quality estimation, we used extracted rationales and compare them to actual machine translation errors, and we found actually that it works quite well, and that was a paper published in Findings of ACL this year with collaborators from Sheffield, Marina, and Lucia from Imperial College. Right. So credits. Most of the work that I presented here has been done by George, a PhD student of mine. Unfortunately, good for him, he finished his PhD and now he moved to AstraZeneca. And also there are some other long-term collaborators here, Marina, Lucia, Elias, and Ion, and the team from Athens University of Economics and Business. Thanks a lot.